And then let's formally define electric current. Okay, the electric current is defined as a charge flow per unit time. And then this is how we do it mathematically. Here, I is the typical symbol we use for the electric current. And then it is defined as the time derivative of charges, which means that we differentiate charges with time. Okay, and then we can rewrite this in the integral form. So if you now integrate current with time, then you will get the amount of charge. So here we are integrating from certain between time period, say from 0 to certain period of time. Okay, this will be the amount of charge that have passed, or the amount of charge that have been accumulated in certain device. Okay. And then we already said that the direction of current is same as the net flow direction of positive charges. And you can also say that it is the same as the negative direction of the net flow of positive negative direction of net flow of negative charges. Okay. And then what is SI unit? Okay, remember the SI unit of charges is coulomb, and SI unit of time is, of course, second. And if you divide one by the other, then we get the unit ampere. This ampere comes from the name of a French physicist, André-Marie Ampère. Okay, Ampère, maybe they call it ampere. Okay. Okay, and there's one rule, important rule that you always have to remember whenever you deal with electric charges, and it is a junction rule. And what it says is that the summations of current flowing in and flowing out of a junction are equal to each other. Okay, take a look at the figure on the right side. There is a Y-shaped wire, and this is the junction. Okay, and then here the I0 is coming in, and I1 and I2 are coming out. So therefore, the amount of current coming in, I0, must be equal to the total amount of current flowing out, which is I1 plus I2. Okay, and then no matter what the shape is, here the wires are curved, but it doesn't matter. In the junction, the same rule must be applied. And what it basically means is that the charges cannot be created, or they cannot just disappear during this current flow. So this is directly related to the conservation of charges that we have already discussed in chapter 21, I think it was. Okay, and then let us introduce another quantity called the current density. Remember or realize that the current is more like a flux. We already learned that if you integrate electric field with certain area, then you got this electric field flux, right? Okay, and then remember this current is just like flux, so therefore you can use it. You can write it in the integral form, and then this value J vector is called the current density. And then what it is actually if you differentiate the current with area, then this is actually the current density. And remember, in this integral form, the current density, of course, is a vector. So therefore, it can have components along x, y, z. So therefore, this form, which is a partial differential, represents the current density only along one of, say, x, y, z directions. So you can repeat this along 3 different directions and then get a total current density vector. And of course, in the simple case, most of the time we will deal with the case in which the current density is uniform over the area. For example, here along this area, the current density is constant. Then you don't really have to do the differentiation, and you only have to divide the current by the area. Then you will get the this current density. Okay. And then in real life, we have to realize that conductors are actually not perfect conductors, and even insulators may not be perfect insulators. So we can say all materials and all objects will have limited ability to allow the charges to flow through. So therefore, we need a method to describe how good or how bad this object is in terms of allowing charges to flow. And we do this by defining the resistance. So the resistance is the characteristics of the object determining how difficult it is for the current to flow through inside this object. Okay, and then we define it by this potential difference across this object divided by the current flow. So you can easily understand that if the amount of current flowing is small, then you can say the resistance of this object is large. And if the current flowing is small, if the amount of current flowing is now large, then the resistance is small. That's what you can say, okay? And in fact, this definition of resistance actually comes from the Ohm's law. So what they did was actually not define the resistance, but actually resistance was in fact a proportionality constant inside the Ohm's law, okay? And then we will study this Ohm's law very soon in the next slide, so please wait for it. And what is SI unit? SI unit, we of course have to divide the volt by the ampere, and then we call this ohm and use the symbol of Greek letter omega, okay? And then where do you think this name ohm come from? Of course, it is the discoverer of this Ohm's law, Georg Ohm, who is a German physicist, okay? And then objects with resistance are called resistors. And here many resistors are shown in this figure. And some are small and some are large. So they have different resistance, okay? And then this different resistance depends on what type of material they are made of. And it also depends on what shape these resistors have. So the important thing you have to understand is that resistance in fact depends on the shape of a material. The reason is because current is just like a flux, and resistance depends on the current. So imagine you have a pipe of water going through, and then if the pipe is very wide, then it will be easier for water to go through, and if the pipe is very long, then it will be more difficult for the water to flow. It's just like that. So resistance depends on the shape of the material, just like a pipe, shape of the pipe, I mean. So therefore, it will be very convenient if we have another method to describe this quantity, and which is independent of the shape, right? So this quantity independent of shape is resistivity. So resistivity is now characteristics of the material, not the object, but the characteristic of the material, and it can be independent of the geometry. Okay, this is how we do it. We first begin by having this definition of the resistance, and then realize that the potential difference is equal to the electric field multiplied by the length of this object. And then also realize that current is equal to the current density multiplied by the area of this object, right? So the shape or the geometry is given in these two values, length and the area. And then this electric field and current density are actually independent of the shape. So therefore, we define resistivity as a ratio between this electric field and the current density, right? Okay. And then we realize that actually these two values are vectors. So therefore, we can rewrite this using the vector form as shown here, okay. And then what is the SI unit? So remember, SI unit of the resistance is ohm, and we have a length which has a unit meter. And then we have an area which has a unit meter square, I mean, okay. So therefore, if you summarize it, then the SI unit of resistivity will be ohm multiplied by meter, and then we just call it ohm meter, okay. And then let me introduce another quantity, which is called the conductivity. Well, to make long stories short, conductivity is simply an inverse of resistivity. So if resistivity is large, the conductivity will be small. If the conductivity is large, then resistivity will be small. Okay, and then so basically what it means is that conductivity is again characteristics of the material, determining how easy it is for the current to flow inside the material. And it's not written here, but you can also think about conductance, which is the inverse of resistance. And therefore, what can you say about conductance? Now, conductance is now characteristics of the object, determining how easy it is for the current to flow inside this object, right? Okay, can you understand what I mean by that? Okay, I hope you do. And finally, we will summarize actually the Ohm's law. So basically what the Ohm's law tells you is that the current through a conductor between 2 points is directly proportional to the potential difference across the 2 points. That's what the Ohm's law states. And mathematically, we can write it in two forms. First, delta V equals Ri. So here is directly expressing what is stated just above. So here potential difference and current flow and resistance. I mean resistance is the proportionality constant. And equivalently, you can express it using electric field and current density, and the proportionality constant will be the resistivity. Okay. And in fact, Ohm's law, it was a very useful concept, but Ohm's law is not always true. It breaks down very often. And when does it break down? So Ohm's law may not be true for a large amount of current. So if you have any resistor and try to flow a very large amount of current, then it will break down. Okay. So Ohm's law is not always true. Okay.